Hello dear students, today I am going to demonstrate you the Hall effect experiment. Determination of Hall coefficient of a known semiconductor. So here we are using a germanium chip. Small chip of germanium whose thickness is 0.05 centimeter. Now apparatus list. We are using constant current power supply which is connected with this electromagnet. So this power supply, this current supply will go through the electromagnet. This is the electromagnet. Next, another two apparatus. This one is Hall effect setup and this one is digital Gauss meter. So we are going to change the current from here and we are going to use a sensor, that is indium arsenide, INAS. This metallic sensor, here in between magnetic poles there is a holder. We are going to use this holder and we are going to see change in Gauss meter reading. So this will be first table, the current versus magnetic field. So this will be our first table. So the sensor has been placed. Now we are going to see that in zero current there is some field reading. So we are going to neglect that. So next we are going to change current 0.2, 0.4, 0.6 and we are going to see change in Gauss meter reading. So one by one we have to note down these readings. So we can see that field reading is thoroughly increasing whenever we are increasing the current reading. So this is the first table reading of Hall effect, magnetizing current versus magnetic field. We are increasing magnetizing current and magnetic field is increasing. After last reading, that is 2 ampere current, turn off the Gauss meter. Gauss meter is no more required. We will minimize this current and we are going to turn on the Hall effect setup. Now Hall effect setup will be required and this semiconductor chip will be inside the magnetic field. Now what is Hall effect? Hall effect is a process in which a transverse electric field is developed in a solid material when the material carrying an electric current is placed in a magnetic field that is perpendicular to that current. That means this semiconductor chip, this is the solid material we are using here. So it will be carrying current. So we can see this Hall effect setup, there is millivolt and milliampere. So through milliampere, so suppose we are setting 1 milliampere current. So this semiconductor which is carrying 1 milliampere current will be placed inside this magnetic field and this magnetic field will be perpendicular to that current. This Hall effect was discovered by Edwin Herbert Hall in 1879. So this effect called Hall effect. So see, we have to set the semiconductor inside the magnetic poles and now we can see that magnetizing current is 0 but we are getting some initial Hall voltage reading. This is voltage reading, millivolt. Okay, so this is Hall voltage we are going to measure from here. Okay, so this will be noted down as initial Hall voltage. It will be subtracted from every reading. Okay, so now if we change current, 0.2, 0.4, just like previous table. Current change will be constant since we are going to copy the magnetic field from first table. So, see, if we change current, field reading, voltage reading are changing, it is also increasing. Okay, so this way 0.4, then 0.6, then 0.8, then 1, 1.2, we are going to take up to 2.0, several readings. Whenever this table done, we are going to set another current. First one was 1 milliampere, now we are going to set 2 milliampere current. We are going to take two tables same way for accurate reading, for accurate Hall voltage reading. So this is 2 ampere current. Now here current will be 0 because we are going to measure the initial Hall voltage. Move it voltage side. So this is initial Hall voltage. Now we can see there is a negative sign. This is normal. This negative sign we are expecting because here the semiconductor chip is N type. Okay, so majority carriers will be electron. That is why this negative sign is coming. So next, again we are going to repeat the previous procedure. Again 0.2, 0.4 and whatever the reading will be, the voltage reading will be, the initial voltage will be subtracted from it and we are going to write that as actual Hall voltage. Okay, next is calculation part. The second table, that is magnetizing field versus Hall voltage data. So we are changing magnetizing current, same just like before first table, and change in magnetic field we are copying from first table, and here we are taking Hall voltage data. Okay, so this is the initial Hall voltage reading for current 1 milliampere, for current 2 milliampere. So initial reading will be subtracted from every reading to get actual Hall voltage reading. This one is the actual Hall voltage and this one is the whatever we are getting, that is written as produced Hall voltage. Next, in calculation part, we have to plot two graphs. The first graph is magnetizing current versus magnetic field. So this will be a straight line passing through origin and it will be a verification graph. That means current is, if current is increasing, field is also increasing. This theory verification. Next, the second graph will be calculative graph. We have to calculate slope of second graph. What is second graph? Second graph is magnetizing field versus actual Hall voltage. So we have taken two data for Hall current 1 and for Hall current 2. So we have to plot both the reading at same graph. So it will look like this. Both the straight line will be passing through origin. By calculating the slope, we are getting VH, actual Hall voltage, by magnetic field, that is H. So we are calculating here, slope means VH by H. Now, after calculating the slope from first line and second line, so it will be a slope 1, it will be slope 2. So, what is the working formula? The working formula of Hall coefficient is RH equals VH by H into T by I, where T is thickness of semiconductor and I is for slope 1, 1 and for slope 2, I is 2. So, RH1 is equals VH by H into T by I. That is our working formula. So VH by H is our slope. T is thickness of semiconductor, that is 0.05 centimeter, and I is for slope 1, 1 ampere, and for slope 2, that is 2 ampere. So next we are calculating this part and we are getting two values of RH. So we are marking RH1 and RH2. Then we are going to take average of these two. So first value was 32 point something into 10 to the power minus 5 unit. And second value was 25.5 into 10 to the power minus 5 unit. So next we are going to take average of these two. So average of these two coming 28.8. So we can write approx 29 into 10 to the power minus 5 unit. So actual value is 33 into 10 to the power minus 5 units. Since we are taking germanium here, so the Hall coefficient of germanium is 33 into 10 to the power minus 5 ohm per Gauss per centimeter. So we can easily find the error. So we are getting 12% error. That is done.